In this example, I'll find the inverse Laplace transform of the expression 7s squared plus 10s minus 1 over s cubed plus 3s squared minus s minus 3, given that this expression equals 2 over s minus 1 plus 1 over s plus 1 plus 4 over s plus 3. So this is our lifesaver here on the right, because we can use the linearity of the inverse Laplace transform. So what we're doing here is we can split this up, this Laplace inverse, into three pieces. So this is the Laplace inverse of 2 over s minus 1 plus 1 over s plus 1 plus 4 over s plus 3. And because of linearity, that's 2 times the Laplace inverse of 1 over s minus 1 plus the Laplace inverse of 1 over s plus 1, and then plus 4 times the Laplace inverse of 1 over s plus 3. And all of these Laplace inverse are the expressions inside the Laplace inverse are of the form 1 over s minus a. And recall from the previous page that the Laplace transform of e to the power at is 1 over s minus a. And so we can compare all of these ones with 1 over s minus a. So for the first one, we have a equals 1. For the second one, we have a equals negative 1. And for the last one, we have a equals negative 3. And so the final Laplace inverse of this expression is then 2 times e to the power 1t, and then plus e to the power negative t, and then finally plus 4 times e to the power negative 3t. And that is our final answer. And the reason this worked is because this expression was already decomposed into simpler fractions. And so, in general, how do we know that such an expression can be decomposed into simpler fractions? And this is where we use a so-called partial fraction decomposition, which you should have seen in Calculus 2, but don't worry, we'll go over some examples here and break it down. So we can rewrite a rational function p of s over q of s as a sum of simpler fractions by using the method of partial fractions. And we're going to consider three cases. So the first case is if q of s consists of non-repeated linear factors. So they can be written as s minus r1 times s minus r2 up to s minus rn. In this case, the partial fraction decomposition has the following form. P of s over q of s equals a sub 1 over s minus r1 plus a sub 2 over s minus r2 plus all the way up to a sub n over s minus rn. Now, if there are repeated linear factors in Q, so let's say that Q is s minus r to the power m, then in that case, the partial fraction decomposition has the form P of s over Q of s equals a sub 1 over s minus r plus a sub 2 over s minus r squared plus all the way up to a sub m over s minus r to the power m. Now, finally, if Q of s has quadratic factors of the form s minus alpha squared plus beta squared to power m, then the partial fraction decomposition has the following form, and I'll just focus on one of the terms here. So you then have a1 times s minus alpha plus beta times b sub 1 over s minus alpha squared plus b squared, beta squared, and then the higher powers of that denominator. Now, one thing to keep in mind here, that all of these three cases, what we assume is we assume that the degree of P is less than the degree of Q. The degree of P of S is less than the degree of Q of S. Now, should you encounter an example where this is not the case, then you can apply long division to get this expression as a, rewrite this expression as a polynomial plus a rational part. So if not, apply long division. Now, this will not occur on the exam because that just adds another layer of work to the problem. So we assume that the degree of P is less than the degree of Q. And in the next two videos, we'll do some examples with breaking down these rational functions to find inverse Laplace transforms.